My phone. Hello everyone, a very good afternoon to all of you. I hope you are enjoying your day and you are still full of energy to attend today's class. See, energy is very important, right? As I say in every class, without energy you will not be able to have that dedication and focus on what you are trying to learn. Okay, so energy is the base of everything. So now, in the previous lecture we covered about dipole, right? We started talking about dipole and we discussed what will be the physical quantities like electric field due to dipole in different orientations. Also we talked about how we will be able to discuss about equilibrium of a dipole in presence of electric field in a region. So today, continuing from there, today let's discuss more about dipoles, how to find electric field due to them for a random point. For equatorial point and for axial point we have discussed in the previous class in lecture number 6, right? So today we are going to discuss about electric field due to dipole at any random point, not necessarily present on axial or equatorial position. Okay, and then we will proceed on to the next topics of electrostatics. As I convey in every class, the PDF of the class will be available in our eCareerPoint app. So kindly download this eCareerPoint app from Google Play. It will be useful for you. Okay, why? Because whatever questions, whatever theory we are discussing here, suppose you are not able to write, you are not able to copy the notes, you can actually revise from those PDFs directly. So better download from there. In the free section tab it will be available to you. Let's proceed for today's class. So let's discuss about electric field due to a dipole at a random point. Okay, at a random point. What I mean to say when I say a random point, see, we have discussed for equatorial position and axial position. So at a random point means it must not be the two of them, and it can be any position with respect to the dipole present here. For example, let's say this is minus q, this is plus q. This time I wish to find electric field due to this dipole at a random position at a random point P. Let's say I am taking P point here, such that if I join this P point from the middle of the dipole, it is making angle theta with horizontal. Okay, the direction of the point P from the middle of the dipole is making angle theta with the horizontal. Now I have to find electric field due to this dipole at point P. I know dipole moment for this dipole will be in which direction? Horizontal direction, because I have placed minus q here, plus q here. So along the line of charges plus q and minus q, there will be a dipole moment from minus q to plus q. From here to here there will be dipole moment like this. This dipole moment is P. P can be written by, see, P and P are becoming same. Let's consider this point as something else. Let's say this point is S. Okay, this point is S. So we are finding electric field at point S due to this dipole, such that dipole moment is denoted by P. Okay, now this P can be written as Q, that is charge, magnitude of charge, into distance between them. How much is the distance between them? 2a. So Q into 2a is the magnitude of dipole moment P. Okay, so now for finding electric field due to this dipole at point S, I should be able to use the formulas which I have derived for equatorial and axial position. Okay, so if I have to use those formulas, I should be having dipole moment which is perpendicular to this line, and I should be having dipole moment which is along the line, because for along the line dipole moment S will be axial point. For perpendicular to the line dipole moment S will be equatorial point. If you are not able to understand what I am trying to convey, focus here. This is my dipole moment P. I am taking two components of this dipole moment. How? Focus. So this is a direction perpendicular to this line. Now if this is the direction of P, in this direction along this line the direction will be, the dipole moment will be P cos theta. If I have to know what will be the component of dipole moment in this direction perpendicular to the line joining middle point to S, I will take component like this. If this is P cos theta, this component will be P sin theta. Is that clear? Now what we can convey here, is now I am having two components of dipole moment, P cos theta and P sin theta. So we can say for P cos theta, S is axial point, right? And for P sin theta, S is equatorial point. So for both of them we already remember the formula. Do you agree or not? We already remember the formula for dipole moment in case of a point present at axial position, and also we remember formula for dipole moment in case the point is present on equatorial position. So what we can say, S is equatorial point, S is axial point. What we can say here is electric field due to this P cos theta will be in this direction, that is in the direction of dipole moment P cos theta, E axial, or you can say E P cos theta. Electric field due to this P sin theta at point S will be opposite to P sin theta, that is E P sin theta. So now we are having two components, E P sin theta and E P cos theta, okay, for point S. So what I will just suggest, that we can write the magnitude of E P cos theta, electric field due to P cos theta, that is at axial point S for P cos theta. We can directly write the formula. How much it is? 2 kp. Dr. Mohammed, hello, how are you? E P cos theta is equals to how much? 2 kp. P means dipole moment in the axial direction. What is dipole moment in the axial direction? P cos theta. So 2 kp cos theta, 2 kp cos theta by r cube. Let's say the position of S from the middle of this dipole is r distance away, okay. So I am taking this distance as r, and distance cube we are writing when we are writing dipole moment electric field, okay. So EP cos theta is equals to 2 kp cos theta by r cube, and if you are supposed to write EP sin theta, electric field due to P sin theta at S, that will give you K dipole moment P sin theta by r cube. So now we are having two components. How? Focus here. This is component 1, this is component 2, and they are perpendicular to each other. So somewhere in between them, somewhere here, the resultant electric field will be present, E net, okay. E net will be present in between EP cos theta and electric field due to P sin theta. So how we are supposed to find that? E net is equals to EP sin theta plus EP cos theta, EP sin theta whole square plus EP cos theta whole square under root, okay. Because the two vectors are perpendicular to each other, if I write a square plus b square plus 2ab cos 90 degree, so 2ab cos 90 degree term will not come because they are perpendicular, and that's why I can directly write net electric field by these rectangular components. How? Square of this plus square of this under root will give me directly the magnitude of net electric field due to both the components of electric field. Is that clear or not? So from here we can say E net is going to be equals to EP sin theta whole square means Kp sin theta by r cube. That means Kp by r cube will be common. So Kp by r cube I am taking common outside, and inside what will be remaining? Sin square theta will be remaining plus EP cos theta whole square means 2 cos 2 kp cos theta by r cube. In this kp r cube by r cube I am taking outside 2 cos theta whole square. 2 cos theta whole square I am writing here. So in this case what we can say, E net is equals to kp by r cube under root sin square theta plus 4 cos square theta. So 1 cos square theta will be taken along with sin square theta. Sin square theta plus cos square theta will give us value 1. We already know, right? For any value of theta, sin square theta plus cos square theta is an identity that is equals to 1. So we can directly use that from trigonometry, and we can write this net magnitude of electric field at point S equals to how much? E net is equals to kp by r cube under root 1 plus 3 cos square theta. Is that clear? All of you understood? Let me highlight this for you. This is the result which we are getting. This is the electric field, net electric field due to the dipole at any random point located at angle theta from horizontal. Let's proceed. Now, net electric field magnitude is fine. What if we are supposed to find angle of net electric field from horizontal? Okay, I wish to know, like this was the situation, na? I am again drawing the situation. Minus q plus q, the distance between them is 2a. This is point S. At point S there will be EP. If this was P in this direction, this was angle theta, this was P cos theta, and this is P sin theta. Just now we have discussed, right? Now EP cos theta is in this direction, EP sin theta is in this direction, because this is equatorial point for P sin theta. Now the resultant of these two is E net. Let's say this E net is making angle alpha from here. Let's say this E net is making angle alpha from EP cos theta. No problem. If this E net is making angle alpha with EP cos theta, let me draw a horizontal parallel, a line parallel to horizontal. What I can do, if this is angle theta, this angle is also theta. Okay, if this is angle theta, this angle is also theta. So what we can suggest from here, we can say that if E net is making angle alpha from EP cos theta component, then we can write directly tan alpha is equals to electric field due to P sin theta divided by electric field due to P cos theta. This will give us kp sin theta by r cube divided by 2 kp cos theta by r cube. So this will give me tan theta by 2. Okay, this is giving us tan theta by 2 as the value. Now tan alpha is equals to tan theta by 2 we are getting for the angle made by net electric field with EP cos theta. This is tan alpha, tan theta by 2. Okay, now what is the condition? Now I am asking you one question. What is the question? Find condition such that E net above is perpendicular to dipole moment. Find conditions such that E net above is perpendicular to dipole moment. What is the direction of dipole moment? Direction of dipole moment is horizontal. See, like this. Now I am trying to find the condition such that this E net is exactly perpendicular to this horizontal direction. How is it possible? We know that the angle made from horizontal by this E net is given by theta plus alpha. So if you ask me that if E net is perpendicular to horizontal, we can directly say that theta plus alpha must be equals to 90 degree. Do you agree? Theta plus alpha must be equals to 90 degree for satisfying this condition. Do you agree or not? If this is so, we can say alpha is equals to 90 degree minus theta. If we take 10 from both sides, 10 alpha is equals to 10 90 degree minus theta. So 10 90 degree minus theta will become cot theta. 10 alpha will be actually equals to how much? 10 theta by 2. 10 theta by 2 is equals to 1 upon 10 theta, because I have written cot theta on the right hand side. So from here I am getting 10 square theta is equals to 2, or 10 theta is equals to plus minus root 2. This is the condition such that E net is actually perpendicular to horizontal or perpendicular to dipole moment. I hope all of you understood it clearly. No problem. Let's proceed further. Now see, dipole placed near a long uniformly charged rod. Okay, let's say this is our long uniformly charged rod, infinitely long, and the charge density on this plus charges are present all over the rod, and the charge density is given by lambda coulomb per meter. Okay, here in front of this dipole is placed. Dipole can be placed in horizontal direction like this, minus q to plus q. Okay, dipole is placed in horizontal direction. Let's say this is our case 1. No problem. Case 1, when we have placed or we have taken the orientation of dipole like this. Now what we can say about this? See, there will be electric field due to this infinite rod or long rod in the region where dipole is placed, right? So that electric field is changing with distance. Why? Because we know that electric field due to this is given by 2k lambda by r. R is the distance from the infinitely charged rod. Okay, r is the distance of the point from this rod. So electric field is regularly changing. So if you say that electric field here is E, then electric field here will be E plus dE. I don't know how much change it will be. I am just assuming that if electric field here E is E at this position, then electric field at another position will be E plus dE. So in that case we can say that the force experienced by this charge can be written as Q into E plus dE in right direction, and force experienced by this negative charge will be given by QE in this direction. Okay, so on this short dipole, let's say this is a short dipole of length dr. This is a short dipole of length dr. No problem. If this is a short dipole of length dr, I can easily write that dF is equals to force, net force experienced by this dipole due to the electric field present due to this infinitely charged rod. I can tell you that net force can be given by Q into E plus dE minus QE, because they are opposite to each other. Okay, so from here I am getting Q into dE. Can I write this Q into dE as Q into dr dot dE by dr? No problem. Now multiplying by dr and dividing by dr, I have multiplied by dr and divided by dr. Now from here what I am getting is q into the distance between the charges minus q and plus q. That is actually dipole moment, right? That is dipole moment. P is equals to q into dr, that is dipole moment. So I am writing q into dr as dipole moment. So you can tell me easily that F is given by P dE by dr. F, that is force on the dipole, is given by P dE by dr. No problem. E plus D not understood. Dr. Mohammed, focus here. See, electric field due to this infinite charged long rod is given by 2k lambda by r. Do you agree or not? So I have assumed that electric field here on the left hand side is E. If electric field here on the left hand side is E, electric field at a distance dr from here will be slightly changed. How much change? I don't know, right? So I have taken that electric field which is at the point very less distance from the previous point. I have considered that as E plus D, thinking that there will be slight change in the electric field at the other point. Okay, so here I considered E, and at a point which is very nearby, which is at a very less distance from here, I have considered E plus small change in electric field dE. Okay, and that's how I have derived that force experienced by this dipole is coming equals to P dE by dr. No problem. Clear? Okay. So this expression you have to remember, it will be useful for us whenever we are doing some questions in future. Okay. So let's proceed for case 2. What is case 2? Case 2 is if we have placed, suppose another orientation is there, when we have placed the dipoles like this, when we have placed the dipole like this, this is minus q, this is plus q, this is positive charge everywhere. Charge per unit length is given by lambda coulomb per meter. So lambda coulomb per meter is given like this, and we again know that electric field due to this is away from the positive charge. No problem, but electric field is given by E is equals to 2k lambda by r. Okay, so let's consider electric field here is E in this direction. Okay, electric field due to this long infinite charged rod will be in this direction, that is going to be E. So in this case we can say that force on charge q will be in this direction, that is plus q into E, and force on charge minus q will be in which direction? This direction, minus q into E. Understood or not? Is that clear? So in this case what is happening, if you ask me what shall be net force, F net on dipole, this will be 0 because QE and minus QE are opposite to each other. So this is going to be 0. So in both the orientations, the expression for finding net force placed on the dipole in electric field region changes. When it is placed in this orientation, F net becomes 0. There is nothing to find. But when the orientation changes to horizontal like this, the expression is given by F is equals to P dE by dr. Is that clear? What is electric field here? Electric field might be due to the external electric field present by any other source. For example, here the source is long infinite charged rod. It can be any source of electric field present, and we just have to see what is the electric field expression of the electric field present in that region, and we have to use this formula P dE by dr for finding force on the dipole. Is that clear? Okay. So both the cases we have discussed. Now, amount of work that is required to be done per unit test charge in bringing it from infinity to that point. So basically what I am trying to define here, we are defining a physical quantity, electric potential. Okay, electric potential at a point. So electric potential is defined as amount of work that is required to be done per unit test charge. Test charge all of you understand, right? Test charge is a very small magnitude charge which is not going to have any impact on electric field which is already present in the region. Is that clear? So test charge is very small charge which is not going to have any impact on the external electric field present in the region. So this is one case definition. What is it? Amount of work per unit test charge. That means for unit charge, amount of work done in bringing it from infinity to that point will be defining the potential at that point. So this is verbally we have written. We will also see how mathematically we can express that. And we also have to remember that conventionally we are considering potential at infinity is 0. Okay, it is not mandatory, but conventionally when nothing else is mentioned, we by ourselves assume that potential at infinity is taken 0. It may be something else as well. That's what I am saying. Until and unless mentioned to you, potential at infinity is assumed to be 0. Okay. So how to express electric potential mathematically? Electric potential at a point. So what I am doing, let's say this is a charge Q, capital Q. There was a charge small q at infinity. We are bringing that small q from here to here at a distance r from capital Q. So this is small q placed here. No problem. From where we are bringing it? We are bringing it from infinity position to here. Okay. Now what? They are telling us that this is the work done in bringing a unit positive test charge. Okay. We know that work done by external force can be expressed as del U. Work done by external force can be expressed as change in potential energy. If work done by external force is expressed as change in potential energy, either we can use potential energy expression here, but till now we have not discussed potential energy, right? So other than that, if I have to say what will be work done by external force, then I can mention that at any random distance r, k q by r square, that is the force acting on this test charge due to this plus q positive charge. dr, we are bringing it from infinity to r. Okay, so from here what we are getting, k q by dr upon r square will give us integration as minus 1 by r infinity to r. So what we can say, k q minus 1 by r minus 1 by infinity. So this will give us, so what else actually we are writing? We are writing that force acting on this plus q was away from the positive charge. This is the direction of force. Okay, and we are bringing the displacement like this dr. So there will always be a negative on the outside of this integration. Okay, a negative on the outside of this integration. So from here I am getting plus k q by r, plus k q by r. This is given as work external in bringing the charge from infinity to a distance r from plus q positive charge. So from here I can say, according to definition, what we had written according to definition, amount of work per unit test charge. That means I will divide the work done by test charge, amount of test charge, and I already know what is the amount of test charge. Amount of test charge is small plus q. So work done by external force divided by test charge q naught or q is equals to how much? How much we are getting from here? kq by r. kq by r. This is what is given as potential V at a point r. Okay, or if you don't wish to directly put this as 0, kq by infinity. Here I have taken kq by infinity to be 0. Okay, 1 upon infinity becomes 0, right? So I have taken this as 0 mathematically. No problem. So this is the potential we are getting at a random position r due to a point charge. Vr is equals to kq by r, potential due to capital Q at a distance r from this charge. Let's proceed further. Now let's find out electric potential due to some standard configurations. Okay, what are the possibilities? If we have to find electric potential due to a point charge, we have already expressed it. How? If this is plus Q, potential at any distance r away from plus Q at point P is given by Vp is equals to kq by capital R. Okay, just now we have expressed in the previous slide. Now one thing we have to consider here, what is that? For multiple point charges, unlike electric field, potential is a scalar quantity. Here distance of charges from point only matters and not their location. In electric field, because electric field was a vector, we were having vector addition of the all components of electric field acting in the region. But now in case of potential, it is a scalar quantity. In this, there is no point of talking or even imagining about direction. So for potential, it will be directly added just like we add volume and mass like this. Okay, just like a scalar quantity. So that's what they are trying to convey. For multiple point charges, potential will be directly added. Okay, potential due to point 1, potential due to charge 1, potential due to charge 2, potential due to charge 3, like this. Okay. So let's attempt one question on the basis of whatever discussion we have had till now. So in this question, what we can do, 2 point charges plus 2q and minus 4q separated by a distance small r are fixed. So let's take 2 point charges. 2 point charges plus 2q and minus 4q. Plus 2q and minus 4q separated by a distance small r are fixed. Then find the potential at a point where electric field is 0, null point. So first of all, I will have to find, is there a point where electric field is 0? Okay, let's search that point. If I take any point in between them, electric field, like suppose I am taking a point here, electric field due to plus 2q will be like this, electric field due to minus 4q will be like this. They are adding up because they are in the same direction. Okay, so there is no possibility of finding a point where electric field is 0 in between the two charges. Where else I will find? Then next I will be able to find it near the smaller charge. Why? Because if I consider something here, then I will not be able to compete with the small charge plus 2q, cancelling minus 4q force or electric field. Is that clear? We are supposed to find the point where net electric field is going to be 0. That means electric field due to minus 4q and electric field due to plus 2q must cancel each other. That will be possible only and only when the point is nearer to the smaller charge, because the bigger charge will manage even if the distance is high. Even if the distance is far, the bigger charge is going to manage. But for smaller charge, it will not be possible to compete with the magnitude of this electric field due to minus 4q when the point is nearer. So my common sense tells me that point is somewhere here. Let's say this is the point of r distance away. Not r distance I have already taken in between them. Let's take something else. Let's say this is small a distance away from plus 2q. No problem. Now if you ask me what will be the direction of electric field due to minus 4q at P, it will be towards minus 4q. So electric field due to minus 4q in this direction. Electric field due to plus 2q at point P will be in this direction. Electric field due to plus 2q. Now electric field due to plus 2q equals to electric field due to minus 4q, because that's what we have to find now. Null point we have to find. Null point means where net electric field comes equals to 0. Okay, So where net electric field is coming equals to 0, there I am trying to balance the component of electric field. So, or you can say magnitude of electric field due to both the charges, minus 4q and plus 2q. So now what I am doing, due to plus 2q, I can write k charge by distance square, a square, equals to k charge is how much, 4q, by distance square is how much, r plus a whole square. Okay, so this we are supposed to balance. Let's cancel k along with k, q along with q. 2 is cancelling 4 and coming 2. Okay, so from here I can write r plus a whole square is equals to 2a square. So from here I can get r plus a is equals to root 2a. No problem. So from here I am getting r is equals to root 2 minus 1 into a. Root 2 minus 1 into a. So this is going to be our answer. What will be the value of r? No, what will be the value of a? Value of a will be r upon root 2 minus 1 from charge plus 2q. Now, is this the final answer? Is this the answer we are supposed to have? No, right? We are supposed to find out what will be potential at this point, because now I understand that this point P is the location where net electric field is coming 0. So that is our null point. At that null point we are supposed to find out potential. So let's find out the potential. Sir, we have to put minus 4q. No, see here, Dr. Mohammed, focus here. I will put minus 4q when I am adding them vectorially. Here what I have done, I already know the direction of electric field due to minus 4q. I already know the direction of electric field due to plus 2q. So in the direction, I have already clarified that E4q is in right direction, E2q is in left direction. So once we are having a clarification about direction, we can directly equate them. And when I am equating them, I am equating only the magnitudes. Okay. So there is no confusion about direction here. Okay, Dr. Mohammed, understood? So when we are writing electric field due to minus 4q, we are just writing the magnitude of electric field due to minus 4q. We are not concerned about direction. Okay, because direction we have already considered when we have equated the magnitude of electric field due to both the charges. Now, once we get the value of A, that is r upon root 2 minus 1. If I simplify this, I can get A is equals to how much? Root 2 plus 1 into r. If I rationalize, multiply by root 2 plus 1 denominator and numerator, I will get root 2 plus 1 into r. Okay. So from here what I can do, I can get this as Vp, potential at point P, is equals to K2Q by distance A. Okay. Plus K minus 4Q by distance R plus root 2 plus 1 R. So R plus root 2 plus 1 R. Okay. So this is going to be the potential, or you can say K 2Q divided by root 2 plus 1 into R. Root 2 plus 1 into R minus K 4KQ divided by root 2 plus 2 into R. So this is going to be the potential. Is that clear? No problem. Calculate on your own. Let's proceed further. So till now we have discussed about finding electric potential due to a point charge. Okay. And we have done problem according to that as well. Now electric potential due to a thin ring of uniformly distributed charge. So let's make a ring now. Let's take a ring. This is my ring. Let's consider a point on the axis of this ring here, a point P. Okay. charge is distributed all over the surface of the ring, like this, plus plus q plus 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 everywhere, charge is distributed uniformly. Now if you ask me, if I take any small element here, the charge here is dq, let's say, so I can say at this point P, dV potential due to this small charge will be k dq divided by distance. How much is the distance? If the distance of point P from the axis of the ring is x and the radius is capital R, I can tell this distance is r square plus x square under root. So if you tell me what will be the potential due to an element of charge dq, I can directly write k dq divided by distance of dq from point P. And what is the distance? Under root of r square plus x square. So from here we can easily write that the total potential, the potential due to the total charge present on the ring will be added up directly. So we can say this dq will become q and this vp will be equals to k total charge q. Suppose if total charge is plus capital Q, I can write kq divided by distance under root r square plus x square. This is going to be the potential at a point present on the axis of the ring. Okay, at a point present on the axis of the ring. Now if I have to find electric potential due to a uniformly charged spherical shell, what we are supposed to do in this? For an outside point, for an inside and boundary point. See, for an outside point, how we are supposed to write electric potential? Suppose positive charge is distributed all over the surface, plus q. For this, suppose I am taking a point P outside of this spherical shell. If I am taking a point P outside of this spherical shell, what I am supposed to write? I am supposed to write directly that the whole charge is assumed to be concentrated at center. What is the total charge on the surface? The total charge is plus capital Q. If I assume that the total charge on the surface is plus capital Q, concentrated at the center, then at point P I can directly write that for x, that is x distance of point P from the center, for x greater than r, we can directly write kq by x as our answer. Okay, potential at point P will be kq by x for x greater than r. Suppose if we are considering a point which is present on the surface or inside, which is present on the surface or inside, the potential will be how much? kq by r only. Now you might be thinking that inside no charge is present, how potential can be there? Your mind might tell you, if inside charge is not present, no charge is present inside, how you are saying that potential inside will have some value? Then we have to go back to the definition of electric potential. What was the definition of electric potential? Definition of electric potential was work done in bringing the charge from infinity to that point. Where is our point this time? Our point is an inside point. Let's see here. Here we are having an inside point Pi here, or we are bringing the charge from infinity to P in. From infinity to P in we are bringing the charge. Okay. If we are bringing the charge from infinity to P in, work done will be from infinity to surface and then from surface to P in. So I am just saying work total from infinity to P in will be actually equals to work done from infinity to surface plus work done from surface to P in. Work done from surface to P in will be 0. Why I am saying work done from surface to P in will be 0? Because there is no force present on the inner side of this sphere. There is no force present on the inner side of this sphere. Why? Because there is no charge present inside the shell. If there is no charge present inside the shell, there will be no force present inside the shell. If there is no force due to anyone inside the shell, there will be no work done. But according to definition, at that point we have to write the total work done from infinity to that point. That means out of the total work done from infinity to point P inside, work done from infinity to S will be counted, and for surface point as well the same work will be counted. That's why the value of potential is same for surface and inside point, because work done is same from infinity to surface and work done is same from infinity to inside point, because inside no work is done. So whatever is done, work is done till the surface point becomes our value for the work done. Understood or not? I hope you got it in your mind and you are able to clarify easily that why potential inside will not be zero. Potential inside will be whatever potential is present on the surface, because the same amount of work done will be there from surface infinity to surface as we are having work done from in case of infinity to inside point, because inside there will be no work done. All the best. I hope you understood everything we discussed today. Keep practicing more and more problems related to the concepts which we are covering. In next class I will cover the high number of problems as compared to today, because today we were supposed to have discussion on the theory part more. Okay, once now we have covered, we will be covering more problems in the next lecture, in the upcoming lecture. So be prepared. Please revise. Download this PDF from eCareerPoint app. eCareerPoint app you can download from Google Play. In the free section tab you will find the PDF from here. Okay, so revise all the lectures till now so that we are able to smoothly and very quickly do all the problems related to the concepts which we are covering here. Okay, all the best. Have a nice day.